Hello everyone, again, Mr. Cruze here. Welcome to another chapter 7.1 to 7.5 review. This is for your quiz, which is tomorrow, April 9th. This is a re-quiz from the one before spring break, so hopefully you do better on this one. So remember, you now have access to these videos as well as the ones from the original review for this quiz. Alright, so use your resources wisely. Okay? So let's start off by graphing some. You'll notice mine has the t-tables unlike yours. Okay, we'll deal with that as we go. But y equals 3 times 5 to the x. Well, I'm going to make this a little easier. Let's ignore the 3 for now. Okay, we'll come back to it. 5 to the x. I can graph 5 to the x. The x coordinates I'm going to use are -2, -1, 0, 1, and 2. And when I plug them into 5 to the x, 5 to the -2nd, which is very easy to do on your calculator, is 0.04. 5 to the -1st is 0.2. 5 to the 0 is 1. 5 to the 1st is 5. And 5 squared is 25. Okay? But that's not what I'm trying to graph. I want 3 times 5 to the x. Well, the question is, does it really change the x values I plug in? And the answer is no. Either way, I'm still going to do 5 to the x. I'm just going to multiply basically whatever I get out of 5 to the x, which happens to be these y coordinates. I'm going to multiply it by 3. So I'm going to take all these y coordinates and multiply them by 3. Okay, so that means 0.04 now becomes 0.12. 0.2 now becomes 0.6. 1 now becomes 3. 5 becomes 15. And 25 now becomes 75. I just took all the y values we had before and multiplied them by 3. Notice the x's did not change. So here we go. -2.12 is right there. -1.6 is right there. 0, 3, and then 1, 15, and 275. Remember, those are a little off our graph. I'm not expecting you to graph those. I just want you to get the best looking graph that you can. It's probably not steep enough. Make sure it actually goes through all your points. There we go. That looks a little better. Remember, this has a horizontal asymptote at y equals 0, so your graph should not go through there. Okay, so it shouldn't, look like that or something. All right. Let's graph this one. Y equals log base 4 of x. Okay, this one's a little different. All right, you'll notice on this one we didn't have to switch anything. We just plugged things in and went. The logs are slightly different. Okay. The first thing I have to take care of is switching the x and y. So you might want to write this. If you're trying to graph a log, you probably want to switch the x and y. Okay? Might want to write that down. So, let's do that. So, x equals log base 4 of y. I'm going to bump the base to get rid of the log base 4. So, we're graphing y equals 4 to the x. Okay? Which is really easy. It's just like this one, kind of. Still use the same x values, -2, -1, 0, 1, and 2. You plug them in. 4 to the -2nd, I believe, is 0.0625. 4 to the -1 is 0.25. 4 to the 0 is 1. 4 to the 1st is 4. And 4 squared is 16. But that's not what we're trying to graph. This is the t-table for 4 to the x. We want this t-table. What was the first thing we did? We switched the x and y. So what's going to be the last thing we do? Switch the x and y's. So here's the t-table we're really graphing, and we're just switching it up. So now the -2, -1, 0, 1, and 2 over here, and the x's are now over here, 0.0625, 0.25, 1, 4, and 16. I'm going to graph it. 0.0625, -2 is right there-ish. 0.25, -1 is right there-ish. 1, 0. 4, 1, and the other one's too far away to graph. So draw the best looking curve you can. Just like this one had a horizontal asymptote at y equals 0, this one has a vertical asymptote at x equals 0. Okay. By the way, in general, for the most part, most of our exponential graphs are going to look something like this. Sometimes they might look like this, but that's rare. That's when this number is less than 1 and greater than 0, right? For the most part, these logs will look like this. Okay, they'll basically look like, kind of like hooks is what I think of. They kind of go up like hooks. Okay, let's practice some where we have to move them now. So if I have y equals 3 times 2 to the x plus 2 minus 3, I'm going to start off by just doing 2 to the x. We'll start off that simple. Negative 2, negative 1, 0, 1, 2. So I plug those in. 2 to the negative 2 is 1/4, so that's 0.25. 2 to the negative first is 1/2, so that's 0.5. 2 to the 0 is 1. 2 to the first is 2, and 2 squared is 4. But that's not what I want. I want 3 times 2 to the x, right? So what am I going to do with all my y-coordinates? Multiply them by 3. So this will be 0.75. This will be 1.5. This will be, I might as well go ahead and do it, 3, 6, and 12. Okay? You notice we're doubling each time. Why? Because it's 2 to the x. Anyway, there's that. Again, that's not exactly what I want either. I need to shift it. This plus 2 tells me I'm going to go left 2, and this minus 3 tells me I'm going to go down 3. Well, left 2 means subtract 2 from x, and this down 3 means subtract 3 from y. So all of our x-coordinates we're going to subtract 2 from. So that's pretty easy. Negative 4, negative 3, negative 2, negative 1, and 0. All your y-coordinates you're going to subtract 3 from. So 0.75 minus 3 is negative 2.25. 1.5 minus 3 is negative 1.5. 3 minus 3 is 0. 6 minus 3 is 3. And 12 minus 3 is 9. Okay? Graph that, and we're good to go. Negative 4, negative 2.25, something like that right there. Negative 3, negative 1.5. Negative 2, 0. Negative 1, 3. 0, 9 is a little bit off our graph. And this one, you'll notice, has a horizontal asymptote because it's exponential of y equals 3. Now, where'd that come from? It came from right there, that minus 3 at the end. Remember, we shifted everything down 3, so that included the asymptote that was at 0. All right? And this one's probably the hardest one, the log, where you have to shift it, right? So, again, with logs, switch the x and y. So let's do that. X equals log base 3 of y minus 2 plus 4. I'm going to subtract 4 from both sides. And then I'm going to bump the base. So 3 to the x minus 4 equals y minus 2. So really, y equals 3 to the x minus 4 plus 2. That's what we're going to make a t-table for, and then we'll be able to flip the x and y, and we're ready to go. So 3 to the x, we'll start with it. Again, negative 2, negative 1, 0, 1, and 2. On your calculator, 3 to the negative 2 should be 0.1 repeating. 3 to the negative 1 should be 0.3 repeating. 3 to the 0 is 1. 3 to the first is 3, and 3 squared is 9. Let's move this, though, just like we did this one over here. This one tells me write 4, so I'm going to take the opposite of what I see. I'm going to add 4 to all x's. So add 4 to x, and we're going to add 2 to the y's. So add 4 to all the x's, well, that's pretty easy. So it now becomes 2, 3, 4, 5, and 6. Adding 2 to the y's yields 2.11, 2.33, 3, 5, and 11. But that's the graph of this. We don't want that. We want the graph of the log equation. So what did I do to begin with? I switched the x and y. So I have to end by switching the x and y one last time. So we get 2.112, 2.333, 3, 4, 5, 5 is easy switch, and 11, 6. So let's graph it. 2.112 is right there. 2.333 is right there. 3, 4, 5, 5. And the other one's too far away to graph. There you go. Again, you'll notice These exponential ones, for the most part, have this kind of growth shape, whereas these log equations have more of a curved hook, I think. All right. Number 5, write 2 to the 4th equals 16 in logarithmic form. Okay, logarithmic form. We're going to try and get rid of this exponent. So to do that, we need to get rid of this base. So I'm going to log it. I'm going to take the log base 2. And you might be saying, Mr. Cruze, why are we doing log base 2? I'll show you why. Great question. Log base 2 of 2 is actually 1. And remember, a property of logs lets me bring the 4 out front. So for all intents and purposes, this log base 2 of 2 cancels. And you're simply left with 4 equals log base 2 of 16. And that's it. It's that simple. This was exponential form. This is logarithmic form. Okay, it still has the same information contained in it. All right. The thing is, you want to take the log base whatever number this is right here. So in this case, it was log base 2. In other cases, it might be some other number. 6, 7, and 8 kind of rely on a certain formula known as change of base formula. Basically, what it says is if I have log base b of a, that's the same as log of a over log of b. And it doesn't matter what base those are in. So this log base 5 of 125 is actually log of 125 divided by log of 5. And let me show you how to plug that in your calculator. Very simple here. You type log 125 divided by, and make sure you close parentheses there, divided by log of 5. And it's 3. Simple enough. Calculator work, if you ask me. All right. Number 7, basically same principle. Only this time you're going to take log of 1/9, and you're going to divide by log of 3. So let's try that out. Log of 1/9 divided by log 3. So we get -2. Okay. And this one's pretty simple. You can do it a couple different ways. You can do log of 8 divided by log of 2 minus log of 2 divided by log of 2 plus log of 4 divided by log of 2. You can do it that way. Log of 8 divided by log of 2, I think you'll find, is probably going to be 3 minus log of 2 divided by log of 2. That's easy enough. You don't even have to have a calculator for that. It's 1. And log of 4 divided by log of 2, I think, will be 2. And then it just becomes a matter of, can you add and subtract? 3 minus 1 is 2, plus 2 is 4, is your final answer. By the way, an alternative approach to this one, you could certainly combine these into a single logarithm and then evaluate it. Since they all have the same base, subtraction becomes division. So this is actually 8 over 2. So 8 over 2 is actually 4. And then if you remember, addition is actually multiplication. So log base 2 of 4 times 4 is 16. And then I can do that little trick, log of 16 divided by log of 2. And you'll find we get the same answer we got before, 4. All right?